section. The Laplace transform, I'm going to give about 1 lecture hour, maybe more than 1 lecture hour to review the Laplace transform. And these methods will be prepared for us to deal with the excitations due to non-periodic functions. Okay, and the vibrations response to non-periodic function, this is the most general situations. And in terms of calculation, this is the most rigorous and sometimes very challenging. This will be the second part of the chapter 4. Okay, if you have time to look over the contents of the chapter 4, basically it's divided into 2 portions. The first portion is the excitations, X harmonic or periodic, and that's we've been done last week, and that is what you are exercising in the 2 homeworks. The second portion, the excitation can be arbitrary, in arbitrary form, and arbitrary, that means in terms of continuous functions, and that can be non-periodic, and that can be random. Okay, but here we don't talk about the random signal. We don't talk about the random excitations. So for the second part, when the external loading is a general functions, and which not necessarily be periodic functions, then we need to come up with some generic formulations to describe the system response to such a loading. So this is the second part. This will give us the preparation for the second part of the chapter 4. And to solve for the response of the system to the general loading, so here we have mx dot cx dot plus kx and equal to ft. And where the ft is a general function. And I would say general continuous functions in time domain. Okay. So basically the general function not guaranteed it's going to be periodic anymore. Okay. And examples of ft can be like this. For example, the impulse and the impulse with certain magnitude, say 0. And by definition, the impulse function basically is this. The force applied in a delta t usually is very small. So that is the impulse. Basically, is boom. Okay. And for this case, the impulse is delayed by, for example, here is t0. So basically, the impulse won't be applied until the t0. So this is called the delayed impulse. Another example can be this is a constant signal. So this is called the step functions. Okay, for this one, basically the force maintained as a constant right at the beginning of the loading. And this is not quasi-static, this is constant. So right away at the beginning, we just apply the loading to the magnitude remaining there. For example, like this, basically this is apply the constant until a certain period and then we drop. So basically this is the, it's not pulse. The pulse, that means the pulse will continue coming up. This is not pulse, okay. And another example, so say the slope equal to whatever any slope. So say C, M, P. Okay. So basically, this is called the run. Loading. Okay, and the most general will be like this. Okay, this is the most general functions. So in the second portion is here, we are trying to calculate the steady state response. At least we will go over the method to find a response to such an impulse loading, to find a response to such a step loading, to find a response to such a loading, and to find a response to the run. And then in general, I will show you a formula, the formulation process, how to determine the response to such a general loading. Okay, and be prepared for yourself and doing the very lengthy, very long calculation, just simply do this one. And once we finish this topic, we over the peak. And then the remaining contents will be a little bit easier. Okay. So that is the second portion, and I expect maybe this one depends. I don't give myself any limit to finish this topic because I want to slow, and usually for this kind of topic is I need to slow, and then so I don't give myself any time limit to finish this topic. And I expect, and those topics can be finished, should be able to finish in 5 lecture hours. I hope so. Okay. So to do so, and I will try to review the Laplace transform method, and this will be the Laplace transform will be the first method, can help us to solve some of the loading type there. The Laplace transform, basically, the concept is this. We are given a certain dynamic system. Okay, the dynamic system basically is something like this, the second order differential equations, and with the initial conditions. So basically those questions, for example, we are given initial conditions x0, and then initial velocity is v0. So basically this one is called the initial value problems. Okay, in mathematics it's called the initial value problems. So Laplace transform is to convert dynamic initial value problems into an algebraic problems. In this way, we can convert our calculation rigors from doing integrations or differentiations into additions or subtractions. Okay, so that is the concept of the Laplace transform. And in this way, we convert from the time domain of the initial value problems from the time domain into an algebraic problems, and that is, we call it in S domain. Okay, S is the parameter we use in Laplace transform. So basically everything we're going to do the algebraic operation in the S domain, so we get a result. Once we have a result, and that is the representation of the steady state response. The steady state response will be, after the algebraic operation, will be in S domain. So to convert, to find our steady state response in the time domain, so once we have done the calculation from here, then you will simply convert inverse Laplace transform to convert the steady state response from the S domain back to the time domain. So basically that is the process. We from here back to here. Okay. We can utilize this as one example, and because in chapter 1 or chapter 2 we already have some little introductions, so let me start over from there, assuming everyone still remember how to do it. And before I go over again the detailed review, and we can deal with this question just based upon our memories of what we have done in the previous chapters, we see how can we do this one here. And so again, we are given these questions, and this is, if you look at the mathematics, this is the second order linear differential equations, and equal to 1, that is not constant. Basically, this is non-homogeneous differential equations, and this one given the initial conditions. Okay, so basically, if you want to directly solve for this DBQ, then you expect your results should have transient solution and particular solution 2 part. Okay, and that is our focus in this topic. If we apply the Laplace transform, if you remember, we have this table. So assuming, let me define the symbols. The Laplace transform of x of t and its counterpart in the S domain, let me use in capital X, and that is function of S. Okay. Laplace transform of the derivative basically will be equal to S multiplied with capital S and minus the initial conditions. Okay, here I give you the formula first, and later I will give you definitions in the next slide. And double derivative in the time domain, S squared minus S okay, so basically this is a constant and this is a constant. So here I underscore that is a constant, and that representing is the initial positions, initial velocity. Usually those initial conditions are given. So with those symbols in mind, then basically I take the Laplace transform of our questions, x double dot plus 3x dot plus 2x equal to 1. So this is our dynamic, the initial value province or our dynamic systems. So when we take Laplace transform, because these are linear systems, so a property of the Laplace transform is that we simply take the Laplace transform of individual components. Okay, so basically this is equivalent to this Laplace transform of x double dot plus Laplace transform of 3x dot plus Laplace transform of 2, oh sorry, this is only 2x, equal to Laplace transform of 1. Okay? So we take the whole thing, we simply take the Laplace transform of the individual one. And also, the Laplace transform is a linear transform. So that means this is the multiplication by a constant 3. So equivalent to say we can have the result 3 multiplied at outside. Okay. In a similar way, the 2 multiply inside, and because that is for linear, so in S, so we can multiply 2 outside here. Okay, so right now we simply plug in all the informations. So let me say this is the 1, 2, 3. You simply plug in the definition of the 3 and 2 and 1. Okay, you simply plug in the definition 3 to 1 into here, then we can see what happens. S squared minus okay, and for the second portion is 3 multiplied with Sx and minus x0 and 2, and that is x. Okay? So we can rearrange the left hand side. I can have the capital X terms together 3s plus 2. and I can collect the initial condition related terms together. So here, since I forgot this one, so that's my typo here. So that's 3 multiply 3. Oops, and sorry what I'm doing. 3. Yeah, I think I forgot this one. Excuse me. I keep doing this wrong. Sorry, I make no mistake. I think this is right.
Is it SX dot EP negative?
SX negative, right? Yeah, thank you.
Should that be 4x naught? Oh, no, you're gonna have that.
Let me double check. I think I gave you the wrong formula. The S should be with this one. Okay, so let's multiply that one. So x dot minus this. Good. Sorry about that. Okay, so once we have this one, then we simply plug in the initial conditions. So that becomes a type of x, s squared plus 3s plus 2. And minus, we plug in the initial conditions, no initial velocity, and initial position equal to 1, so that is s minus 3, and equal to this one. And the plus transform of 1, and later we will see the tables, but here I can give you the result, and that is equal to 1. So maybe here, Laplace of this one equal to s over, so we're using the equation 4, we got this one. So therefore, from here, you can see the capital X will be basically equal to s plus 3. I move the two terms to the right-hand side, and then divide the both hand sides by this. So this is capital of S. Okay. You good? This term representing is a steady state response of our X. And right now we are doing is this. And we are given the initial conditions, and we're taking the plot transform doing the algebraic problems. So compared to this diagram, and on the top here, we're doing the plot transform. So basically that is what we're doing here, okay? And once we obtain the solution of the algebraic problems, this is the solution here. So basically, this one is the result of the solving for x in the S domain, and that basically right now we are here. And one more step, we want to obtain the steady state solutions, and this solution simply is the inverse Laplace transform of what we obtained of the solution here. Okay, and here I can tell you this one, after appropriate operations, this result is equal to 1/2 plus e minus t minus 0.5 e minus 2t. So this is converted into time domain. This is our steady state response. How to do it? We can go to the next slide and begin to review the Laplace transform. So I will keep these things here and see how can we do it later on once we review these. Okay, so this slide give us the definitions how the Laplace transform was conducted exactly. So if we are given any time domain functions, okay, any time domain, and basically continuous, okay, Laplace transform is a result of the integral of that time domain, the time functions, multiplied with e times to the minus t, and integral over t, okay? And that integral taken from 0 to infinity over time domain. So basically in the whole integral, once we conduct it, leaving the s as the parameters, so the result of such an integral will be the function of s. So basically here we're saying this one, the Laplace transform simply is to compute the integral of these expressions. We call that transform. Basically that's the result. So the Laplace transform is a result of such integral, which will be the function of s. Okay. So this is the fundamental definitions. So that means we Laplace transform of any time functions, and simply is a result of such an integral. And by notation, we're simply using the L representing transform and of this function, and we represent it. Usually in Laplace transform kind of operations, we use lowercase to indicate the function in the time domain, and using the corresponding capital case, the representing its counterpart in the S domain. Okay, so that is the general exercise for this. So just like here we have, and we're using the lowercase x representing the time domain, the functions. Its counterpart after Laplace transform, we use the capital. Okay. The Laplace transform, this is the definitions. So any functions, right now we say any function, if you calculate it through this the operation, you should be able to find the expression of the integral. The Laplace transform can only be applied to a certain portions of the time domain functions. It's not all of the time functions. The requirement is such that if the functions satisfy these conditions, okay, then that means the integral not go to infinity, then the Laplace transform of that functions exists. If these conditions violated, then that function doesn't have corresponding Laplace transform, period. Okay, so that is the limitations for the functions we can operate. And most of the time, in the content of our vibrations, the time basically will fit into these conditions. So basically here we assume most of the time functions we deal with should have the time and the Laplace transform. Okay, so here we can do some example here. So for example, we can do the exercise for that one. So for example, if we want to take the plot transform of the exponent AD, okay, and by plugging to the definitions, so basically that is the integral of the functions we are given here, exponent to the AD, and multiply per the definition, multiply with e minus st, we do the integral over t. Okay, t is from 0 to infinity, so we simply do the integral of this one. E minus a minus s t dt. Okay. Are you able to do this one? I don't have my notes. Hopefully I won't make any mistake. So basically this one equal to a minus s, and then 0 to infinity e a minus s and b a minus s t. Right? Okay, so in this way that is a minus s, and then this integral give us is the a minus s of t here, and t from 0 to infinity. Is that right? Hopefully. So this one will be a minus s, and when t equal to infinity,
Because you have to have the stipulation that a is less than s, so that goes to 0.
yeah. So a, we're assuming a is a constant. Okay. So how to proceed? How come? I screw up.
We just have to have the thing on the side where you have to make sure that s is greater than a, right? It's just, it only works for when s is greater than a. I think that's what the stipulation was.
So I can fix the statement
Well,
here.
It's just at the end.
You just take that term e to the a minus s times infinity and assume it goes to 0.
Yes.
And that only happens if s is less than, or a is less than s.
A is less than s. Yeah.
Right.
So when a is less than s, basically this becomes
0.
0. Good. So that helped me to resolve my stuff here. So fitting to these conditions, a is less than s, right? Okay. So in this way, this equal to 0. So that is s minus a. Nice. Yeah, that's what I expected. Okay. And similar way, I don't want to do this again. So you can do it. Okay. This one is more useful. And actually, most of the time, we don't need to conduct this kind of detailed integrations. And we have the tables. And let me try to interrupt the tables to see where I can get it. So here, there's a the Laplace transform tables basically span more than 10 pages if you have any manual. And here I summarized the few common functions will be used a lot in linear dynamic systems, in particular in control and in vibrations. So, for example, this is a time domain functions. This is one corresponding, the Laplace transform is 1 over s. Okay. How you can do it is this. Laplace transform of 1 simply is 0 to infinity, and the function equal to 1, and e minus as and est dv. Okay, so per our Laplace transform formula, that is in this. So if you conducting the things, let me skip the detail, that made me scared. And that should be 1 over s. Okay, so that is reason here. The Laplace transform corresponding part is 1 over s. And for t, that is a ramp functions. So basically, if ft, this is t and this is ft. So if this one equal to t, you can see basically this is a ramp functions and with the slope equal to 1. Okay, and that is the corresponding is 1 over s squared. And this is t to the say square or third power or force. Then basically that is this one. Exponent at 1 over s s over 1 and s minus a. And you can refer to this kind of things. And also we have a sine, cosine, exponent with sine and cosine. And delta, this one delta is called the impulse functions. By definition is this. The delta is called the unit impulse. Unit impulse function is such that the force applied at the beginning when at t equal to 0 and the magnitude equal to 1. And I would say this force applied to very narrow, and this is the delta t. Okay? And delta t is very narrow, very small. And for here, we mean the unit, that means this area equal to 1. If area is not equal to 1, then that basically called the impulse. Okay, area equal to 1, then we call the unit impulse. So you from here you can see, depends on how you control the delta t. If delta t is finite, basically this magnitude is finite. If delta t you can control is very small, basically this magnitude will get big. Okay, but here by definition mathematics, we're using the area to define the magnitude of the impulse functions. So for delta t, that is the unit impulse, and Laplace transform equal to 1. And what is delta t minus a? Delta t minus a is the delayed unit impulse. So this happened at t equal to a. So this is called the delta t minus a. And this one area equal to 1, so it's still unit. So basically the delta t minus a, we call it delayed unit impulse. That means such an impulse was not activated until a time equal to a later. Okay? Okay. So those are the first set of the tables. And that pretty much constitute the majority of the things we're going to see. We're going to use in vibrations. And for the second portions of the table, basically provide some algebraic advantage of the forms. For example, if we have two time functions, f and g, and they are in linear combinations, then the corresponding Laplace transform of the composite one will be such that they are in the same manners of the linear combination of their counterpart. You good? Okay. This is the first derivative of time. So basically, you can imagine this is a velocity. So velocity is the Laplace transform simply is s multiplied with the counterpart minus 0. So basically, that one is what we see here. The Laplace transform of x dot equal to s times capital X and minus initial conditions 0. So that is saying of this formula here. The second one is the nth order of derivative. So basically, this one saying is this. Double derivative. Acceleration for this one is s squared times capital of s. And minus, we follow this one is the s times x0 and minus x, this one. For example, if we have the third derivative, then follow up that pattern is s3 times x minus s squared. When n equal to 3, this is s squared times initial conditions and minus s, initial velocity, and minus this one. Okay, so that is the applications of this formula here. Okay, and you can repeat for n equal to 4 or 5. This one basically saying if a function multiplied with t to the n is converted, the Laplace transform basically is this. First, you calculate the Laplace transform of ft, then you have that f of s. Then in the s domain, you simply do the nth order of the derivative and multiply with these coefficients, then that is corresponding of this form. Okay, so maybe you can try. Let me pick up one. EAT. So we can exercise this one. So it's the Laplace transform. Like this. Okay. So now let us practice one. Tn, TAD. Okay. So we per this formula that has that information. So basically that is minus 1 times n times n's derivative in the s domain. So that is d and dsn s minus a. That's it. You good? For example, if this is 2, then that is d squared. You good? Okay, so that is how to utilize the result. And in a similar way, if you multiply 1 over t, then I have the 1 times the 1 integral, and yeah, follow up. Okay. And this one, basically, let me explain what is this. For example, let me utilize the one, for example, ft is something like this. Say if f now is like this one, okay, this is a time domain. Then what is utilize this notation t minus a, ft minus a. What is this function meaning? So this one is called the Heaviside functions, And when it composed to any time domain functions, basically that is saying is this. This is the when time equal to a, then the response of the function simply is like this. So basically, this is a symbol to denote we delay the operation of such functions. We not start it until a moment later. Okay, that is a delayed form. So another example like this. So say if we have ramp functions and with any slope, whatever the slope c here. So for such a delayed ht minus a, and with the ft minus a, then basically that is like this. Okay, so we simply postpone the operation of the patterns of the function with the same pattern until it hits the moment A. So basically delay it. Okay. This one, so for this one, if we have such a delayed operation, then again, the Laplace transform is this. We know that for this part, this Laplace transform of the constant 1 equal to 1 over s. So in this case, this Laplace transform per our tables here is 1 over s multiplied with this one. So here this has a Laplace transform e minus as times 1 over s. Okay. The next one, a function ft of plus tau equal to this one, basically saying this is a periodic function, and this function have a period equal to tau. So Laplace transform can also handle the periodic functions, and that means whatever we have been learned in the first portion of these chapters, we can also do it using Laplace transform. Okay, so its counterpart of the Laplace transform table, the counter is this one. Okay, and the next one, this is kind of the weird integral. That is we're going to deal with this one. So if we are doing the integral, if we are given two functions, ft and gt, and if we want to do the integral, a spatial integral, something like this. This integral taking tau, and tau is from 0 to, for example, infinity. Okay, and this one we can show this is equal to ft minus tau multiplied g tau. They have the same numbers, the same integral result. Okay, such a spatial integral is called the convolutional integral. And these occupy a big sections in chapter 4. And once we over this topic, then we over the peak of the technical challenge, the rigorous technical calculations. And we're going to talk about this one. But by all means, for convolutional integral, the Laplace transform is simply the multiplication of the individual transformed functions. So that is very straightforward. Okay. So here I spent a little bit of time to share with you and how to interpret the information on this table such that you can utilize the table to do the calculations. Okay. And the final value theorem and initial value theorem, this one, once we use it, I will refer to it. And those things are for more of more for control, not for this class. But later on, once we use it, I will mention that one here. So I would say this table would be useful for the calculations, for doing the everything. So I will come back often to this page and to assist us to do some kind of calculations here. Okay. So I still keep these things in mind. So what is this? So let me write it down the equation here. Okay. So let me try. We can try to solve for this one using the table. We see how can we do it. To use the table, the first step is you have to manipulate the information that the table show up. If you don't have any terms that table provide to you, then just do it by doing something. Okay. So here, let me rewrite. The numerators can be factorized in terms of the multiplication of the two terms. How to do it? Any mistake? I need some help. So that we can have a new sections.
Okay.